Looks like this should be Organic27F. And I'm picking up here with lone pair adjacent to a positive charge, pi bond between atoms of differing electronegativity, and conjugated pi bonds in a ring. I don't think this is going to take us too long, I hope. So we're talking about lone pair adjacent to a positive charge, bond between two atoms of differing electronegative, and conjugated pi bond enclosed in a ring. Okay, each one of those is fairly simple. Where are we at? This one? Okay, this is the example given in the book on page 76. So you got a lone pair and you're adjacent to a positive formal charge. Well, that's not going to be happy. It's pretty easy for this lone pair to jump in here, make a double bond, and eliminate that positive formal charge. And then these are in resonance with one another. So don't forget the brackets and the double-headed arrow. Going on to the problems, 2.27a. I think they give you this and you got to come up with the other one. Here's your positive formal charge on this carbon. You got a lone pair on the nitrogen. It's going to jump in there and make a double bond. And by the way, that'll leave a positive formal charge over here. Remember, nitrogen is in the fifth column. It'll share to get H. There's 2, 4, 6, 8. These are shared. There's a CH3 here and a CH3 here, or a methyl group and a methyl group. But as far as the electrons that nitrogen brought, it brought one from there, one from there, one from there, and those two, so that's 5. When it puts that double bond in here, now it's down to, it owns 1, 2, 3, 4 of those electrons, sharing the other 4. So it's got a positive formal charge. Next example they give you is apparently this one. Got negative formal charge here, but that's not really part of the question at this point. Do have a positive formal charge here, lone pairs. We'll move in there and do resonance with a double bond. Okay. Going on to C, we've got a ring here, an oxygen with 2 lone pairs. You got a positive formal charge on this carbon, so a lone pair will jump in there and make a double bond. That leaves, when you're done though, a positive formal charge here. Don't forget your bracket, don't forget your double-headed arrow. I want to make sure I didn't forget a formal charge back here on this page. No, we're good. All right, next one. All right, if you go up to page 77, there's a nitro group example. It seems to me like we already did this one or discussed it at some point. Nitrogen is up there in the second period. It cannot have 5 bonds. In fact, I'm sure I cut and pasted this somewhere. But if you have, okay, there's a positive formal charge. So this is what we have. And a lone pair. So yes, a little pair of electrons can go in there and jump in there and make a double bond, but nitrogen can't have 5 bonds. You can have 3 bonds and a lone pair is what it normally has. Here it's got 4 bonds. So here it's got 4 bonds. If a lone pair jumps in here, I have to ditch a bond here and make a lone pair over here. Okay, and this would be in resonance with one another. Don't forget the brackets and the double-headed arrow. Okay, the next section, we're going on to pi bonds between atoms of differing electronegativity. This one already, and then the last one. I copied from page 9, there's a table 1.1 of electronegativities. this has only got a dozen or so elements on it. So you need to, Google periodic table of electronegativities and get all of them. But most of what we're doing is organic compounds between these guys right here. Carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, you get it. So this pretty much works. But make sure you're familiar with the table of electronegativities, and you'll find one. All right, so most of the time we've got carbons 2.5, nitrogen's 3.0, oxygen's 3.5, hydrogen is 2.1, although it's not really a player usually what's going on, it's just kind of there most of the time for us. So a pi bond is going to move a pair of electrons up to become a lone pair on a more electronegative atom. In this scenario, if you've got a double bond here and a more electronegative atom, so we're comparing our carbon here to our oxygen here. Oxygen is more electronegative than carbon. Then the electrons can jump up here and make a lone pair. Now if you think about it, this is the opposite of what we had before. Because before we had a lone pair adjacent to a formal charge. And if you looked at what we were doing, we kept making this. Now we're taking this and making the opposite. Well, but they're in resonance with one another, so you should expect that. All right, so if an electron pair jumps out of the double bond up here on the more electronegative element, we end up with a positive formal charge in this case down here, and a negative one up here. So it's kind of the opposite of what we just did. All right, so looking at some examples, you got carbon here, nitrogen here. Nitrogen's more electronegative. So this double bond could give up a lone pair that comes up here. Now we end up with a formal negative charge though, and a formal positive here. Nitrogen has one more electron than it ordinarily would. It's got 1, 2, 3, 4, 5. And then the shared one there is a sixth one. So that gives it a negative formal charge. This carbon is down by a bond, it has a positive formal charge. Don't forget to bracket the double-headed arrow. Okay? In this one, probably if you go back a few pages, you find the opposite of this back there. More electronegative atom is more electronegative than carbon. So we're going to have a lone pair jump out of this double bond. We'll be left with a formal positive charge here and a formal negative charge there. Don't forget your bracket and your arrow because that whole thing is in resonance. Here we've got what's called a bicyclic compound. Those are fun to name. So we have a ring here, kind of a ring there, and a ring here. Actually, this would be tricyclic, wouldn't it? Okay, anyway, never mind. We got a carbon, oxygen. Oxygen's more electronegative. Electrons will jump out of that double bond and onto that oxygen. Gives it a negative formal charge and a positive formal charge on the carbon. Okay, on this particular one, there's a whole lot of molecule here for this little bit going on. This is a carbon and carbon, so you're not going to see what's happening here, because this one is carbon and oxygen. We have a more electronegative atom here. Electrons jump out of this double bond, and you end up with 3 lone pairs, a negative formal charge, and a positive formal charge. In resonance, brackets, double-headed arrow. Same thing, double bond, electron pair come out and go to the more electronegative atom compared to carbon, compared to oxygen, leaving this part, this negative formal charge, this positive formal charge. Okay, last one, 5. Conjugated pi bonds and closed inner rings. We have a ring, pi bonds, and they basically can chase each other around one way or the other and considered as resonance. Okay, so if you look at this, this would be a benzene ring. Each section has double bond character, indistinguishable from the other sections. So even if you could make it where you had a double bond here, here, and here, you're going to get molecular orbital junk going on, and it's going to behave symmetrically all the way around. That's because of resonance. Okay, so this is all identical to this, and this is one way to draw it, just moving the bonds around. So no, I didn't put the curved arrows in there. As a matter of fact, this is, I don't even know if that was in the answer. I doubt that it was. Let me check quick. 2.31. I guess they do have little curved arrows in, because you see this so much, and it's drawn so many times, that you just assume that this is the old benzene ring, and you never put the curved arrows in there, and you never show the resonance, because you see that and you know what's going on. And you could have your curved arrows run the other way. It would be just as correct. Nobody ever puts them in there once you get going with benzene rings. Okay. In this particular one, we got a more electronegative atom than the carbon, so out of the double bond is going to come a lone pair. That'll leave a formal charge down here, but then you can invoke that rule that we had earlier about you're adjacent to a formal positive charge. So you'd have this double bond would give up electrons, or it would move basically over to here, and you could have the formal positive charge here. These all could be in resonance with one another. It is not correct, I don't think, however, to put a double-headed arrow in here, because it has to go through the middle to get there. Okay, and here you have a positive charge adjacent to a double bond, so double bond jumps over here, and then you could have the same thing happen, a positive charge adjacent to a double bond, and then you have the same thing in a reverse. You have a positive charge adjacent to a double bond. You can go the other way. That's why it's resonance. Okay, I feel like I am in the chapter review stuff here. Let me grab my book because I had to use it. Okay, yeah, I'm on page 79 at 2.32, and they have you drawing resonance structures for all of these, and they're all thrown together now. You have all 5 examples here. So, going back here, in other words, what we're doing is, in 2.32, I don't know that they actually tell you this, but you're doing all of these. This is probably a little lone pair on the one that we're about to look at. Looks like it, yeah. Here's a double bond. This is an allylic position. We got a lone pair, allylic lone pair. It's going to move in here, make a double bond. These are going to jump out, make a lone pair. And then we've got a allylic lone pair on this end, so we'll go the other way. Okay. So there's a more electronegative atom on this one. Taking on a lone pair, giving up this double bond. Then we've got lone pair next to a charge, so that's going to run in there, make a double bond. So that's that rule. Okay, here we have lone pair next to a formal charge, so we'll make a double bond there. This could probably qualify as a allylic lone pair, because if this is vinylic positions here and here, you got a lone pair adjacent to that, so form a double bond here. Then you got negative charge, a lone pair here in a allylic position. So So if that jumps in there and makes a double bond, then you've got this one, and then you've got the same thing the rest of the way around. Okay, allylic lone pair. This one, lone pair adjacent to a formal charge, would make it go like so. Then, going back the other way, you have more electronegative atom here, so it's go that way. Okay, this is pretty much the same thing we saw before. This is more electronegative atom here. Once you do that, there isn't, I don't think, a rule that shows this going to here. It's just once you move that over, you'd be short. You'd have to. Be due to the number of bonds. This is a allylic lone pair. Jump in here, make a double bond, it'll give up electrons. And then going the other way, you have adjacent lone pair going in here, and this is more electronegative atom. So you have two rules working for you this way to make it go the other way. Okay, and you get the idea. Well, okay, let's do this last one. Here we've got more electronegative atom, jumps up there. Then we have lone pair adjacent to a charge, so those can jump in there. Okay, and you could reverse those back through. We'll call that for the week, and then jump to the end of the chapter and work on 2.45 onwards. We'll catch up with that later.